Good day, stat students. So today we're going to go over section 9.4 and we're going to talk about proportions slash percentages. So proportions are usually thought of as a decimal, percentages as a percent, right? Just move the decimal point over 2 spots and throw down your percent sign. So we're talking part of the total. What part of the group has a certain characteristic? So proportions are from 0 to 1, so they can't be negative, can't be greater than 1. Percentages from 0% to 100%. So some students go, well, what about a percentage increase? We're not talking about a percentage increase. We're just talking about a percentage of the total. So for instance, you order a pizza. You can eat 25% of it. You can eat 50% of it. You can't eat 125% of it. That doesn't make any sense. All right. So we're talking about part of the total. So we have a sample proportion, which we give the symbol p hat. Please memorize that ASAP. P hat is the sample proportion. Let's focus in on this a little bit. There's a simple little formula for p hat. It's simply x over n. X over n. Where have we heard this before? Number of successes. That's what x is, number of successes. Where have we heard that before? Oh, that's right. That's the binomial random variable. And so x is binomial. That's the numerator. N is the denominator, sample size. And that's the simple little formula for it. And knowing that it's binomial, it's going to help us develop some other things further in these slides. So for example, we sampled 20 students and 9 are female. What percentage of the sample is female? So you look at this and go, okay, well, this is pretty simple. I'm sure all of us can calculate this really quick. But I want you to kind of, instead of just hurrying up and calculating, I want you to think about this for a second. So what would be a success here? A success, since the problem is asking about getting a certain percentage for females, that means every time we find a female, success. All right, so how many successes did we have in our sample? We had 9. That would be x. What is this right here? We sampled 20 students. What is that? That's the sample size. That's n. So here's our x over n. So we have 0.45 or 45%. Now, let's focus in the population proportion. That's a parameter. The sample proportion was a statistic. That's a measurement from a sample. Okay. The population proportion, that's a parameter. That's coming from the population. That's a measurement from the population. Now, don't freak out about this one, but the symbol that we give it is lowercase p. And you might be asking, well, why are we using lowercase p again? We used it with the binomial. Well, obviously, p hat and these proportions, and that for that matter, lowercase p, are all related to one another. Okay, and so we need to develop this a little bit and show you why we are using lowercase p again. So recall how to do this problem. Kind of sit back and see if you can think about how to do this problem. 60% of all US adults have corrective lenses. What's the probability of randomly choosing 15 adults and exactly 8 have corrective lenses? I suppose that's supposed to have a question mark in the end. How would you figure this out? Hopefully you sat back and said, okay, either a person has corrective lenses or not. And that sounds like the binomial. Success and a failure, right? Where it looks like P would be equal to 60%. That's the probability of success per trial. N is 15, and we're trying to figure out the probability that X is equal to 8. And so then we would use our binomial table or binomial formula or StatCrunch to go figure this out. That's not the point here. The point is that I want you to focus in on where it says P is equal to 60%. And we said that, well, okay, based upon the problem, that's the probability of a success per one trial. But notice what I actually said in the problem. I actually said that 60% of all US adults. And then we went ahead and applied that to the success for one trial in the binomial. So that's how probability works. Once we understand the long run probability, we can apply the same probability to just one trial. For instance, I'll give you a simple example. Let's say that we have a coin and we have a whole lot of time on our hands, and we decide we're going to flip that coin an infinite amount of times to figure out the long run probability. Well, you find out that the long run probability is going to be what? Of getting, say, tails. Well, 50%, right? And so what do? After we figure out what the long run probability is, we can go ahead and apply that to just one flip. And so then we can say that the probability of, of getting heads on any one flip is what? 50%. So the population proportion, P, the long run probability, is the same as the probability of success for one trial regarding the binomial. They're exactly the same thing. Because of that, we have to use the same symbol. They're exactly the same thing. So we use lowercase p. Hopefully that makes sense to you. Now, you might be saying, hold on, Doug, I thought you told us that we like to use Greek letters for parameters. That's true. However, I did say there was one exception to this rule, and it's this one right here. So if you went into, say, Microsoft Word and put a lowercase p and then changed it over to a Greek letter, you know what Greek letter is going to pop up? Pi. We already sort of used that in math already. So statistician said, maybe we can't use pi here for the parameter. We gotta use something else here. That's going to confuse students and people. And so what we've decided to do is to use lowercase p for the parameter and p hat for the statistic. That's all, okay? And so it's our one exception. All right, so that was our discussion with regards to proportions in general. Now, this is really the main focus is what's coming up here, okay? So if you kind of said, boy, I kind of knew most of that stuff. Okay, so we're using a symbol, p hat, great. This is really our focus. All right, so I have here's a question. I asked 36 students in the class to randomly sample 10 adults, and you record how many of them have corrective lenses. Then you calculate the percentage or proportion of the 10 adults that have some sort of corrective lenses. All right, so we go ahead and do that, and we find out that student 1 finds 6 adults with corrective lenses. So that means p hat for that particular person, for that particular student, for that particular sample of people turned out to be what? 60%, or 0.6. How about for the second student? We don't expect it to be the same, that percentage to be the same. That doesn't make any sense. We don't expect that percentage to be the same for every student, right? So for student number 2, that student finds 4 adults with corrective lenses. So the p hat for that student, for that particular sample, based upon the people that that student happened to randomly choose to come into the sample, turn out to be 0.4 or 40%. So what are we learning about the sample proportion p hat? This is important. P hat varies from sample to sample. So unlike a random variable like time or like weight, where that varies from person to person. So the time it takes you to get to campus or an individual's weight at any given time, excuse me, that varies from person to person. However, p hat, we're not talking about varying from person to person. P hat actually varies from sample to sample. Every statistic varies from sample to sample. And that's what we're studying, is how these statistics vary from sample to sample. That's what we're going to be studying in this chapter. So p hat for the first person, for our first student, turned out to be 0.6 or 60%. For the second student, it turned out to be 40%. The third person, maybe again 40%. These can repeat itself. So we would have taken a look at all 36, but there's certainly more than 36 possible samples out there. Actually, I put a question mark here because there's a whole bunch of possible samples, each with their own p-hat. Maybe the very last one that we could possibly take turned out to be 50%. So what we're going to do is we're going to take all these p-hats, combine them all together. As long as they have the same sample size, okay, we'll combine them all together into a histogram. Once we do that, we are creating the sampling distribution of p-hat. So we take, so notice here, all these p-hats here had a sample size of 10, since they all had the same sample size. We can go ahead and take all those p-hats and put them into a histogram. All right, all of them, not just the 36 that the students took, all possible. Put them into a histogram, and this histogram starts to exhibit certain characteristics. And this histogram we are going to call the sampling distribution of that particular statistic, in this case, p-hat. The symbol that we use for the sampling distribution of p-hat is p-hat with parentheses around it. That'll be a common thing. That'll be a common thing as we move forward. We always want to learn three things with regards to a sampling distribution for a statistic. By the way, you can only create sampling distributions for statistics, all right? Not for parameters. For parameters, there's only one at any given time. However, for a sample, as we saw, there's a bunch of possibilities out there, all right? So we want to learn three things about any sampling distribution. First one is its mean. Second one, it's standard deviation. The third one, it's probability distribution. So let's start with the mean of the sampling distribution of p-hat. This sometimes confuses students, but it's actually a simple concept. So here's our data again, and I got a simple question for you. Okay, so when we talk about the mean of the sampling distribution of p-hat, what we're talking about is averaging all these numbers, all these possibilities here. You know, the 60%, the 40%, the 40%. So the question is that if we average a bunch of percentages, so when we average a bunch of percentages, the mean of them is going to be what? It's not going to be like 14.7 or 6.8 like X bar would be. It's going to be another what? Percentage. That sometimes confuses people, that a mean of something, of a group of numbers, can be a percentage. Well, if you start with a bunch of percentages and you average all of them, the average of those percentages is also going to be a what? A percentage. Sometimes that confuses students. So I just wanted to make it obvious right now. All right. What we find out is that the mean of the sampling distribution of p-hat, believe it or not, in value is going to be equal to p, lowercase p, the population proportion. Believe it or not, that's all it is. What we find out is that the standard deviation, how these p-hats vary from one another, has a simple formula, all right? It's the square root of p times 1 minus p over n. And you might be asking, Doug, where do these come from? Well, this is a simple little development, okay? This is a simple little development. So I didn't mean for all this to come up all at once, but let me show you here. Let's start here. We know that p-hat is equal to x over n, where x is binomial, okay? Number of successes. So I want to remind you of something. This is one of the reasons why we learned what the mean of the binomial is. So the expected value of the binomial, remember, it was simply n times p. Does that sound familiar? So the mean of the binomial? All right. So if we're trying to figure out the expected value of the sampling distribution of p hat then, meaning its mean, so that's all we're trying to do here is we're trying to calculate the mean, all right, of the sampling distribution of p hat. And so another way of writing that is simply by putting the expected value of p hat. That's what we're trying to do here. All right, so we know that p hat is x over n. N is a constant, and when it comes to expected value, we can just move it outside of the expected value stuff. And so it's really what it turns out to be is 1 over n times the expected value of x. Well, what did we just say the expected value of x is based upon that it's binomial? It's n times p. So yes, substitute that in for the expected value. So what are you left with? You're left with 1 over n times p hat. And let's see, the n's cross out. And what are you left with? Simply p. Okay? So that's where that comes from. It's because x started out as binomial. You're dividing through by n, all right? And so the expected value for the sampling distribution of p hat is just simply the population proportion p itself. That's important. Okay, what about the standard deviation of the sampling distribution of p hat? All right, so we kind of develop it the same way. All right, we develop the same way. And so we have to ask ourselves, well, if x is binomial, what is the standard deviation of x? Remember this? The square root of n times p times 1 minus p. And so you develop it exactly the same way. So you got the standard deviation of the sampling distribution of p hat. We know that p hat is x over n, where x is binomial. The n, 1 over n is a constant. We can move that outside of the standard deviation portion of things. And we say, okay, well, what is the standard deviation of x? Standard deviation of x, where x is binomial, is that. And so we substitute. And so we have 1 over n times this stuff over here. Well, you can see the algebra that I've done here. All this is very much standard algebra. All right. And eventually we get to this. So the standard deviation of the sampling distribution of p hat is developed because we know what the standard deviation is of the binomial, and we're just dividing again through by n. And this is what it turns out to be then. So you can take your time and see how it develops there, all right? But that's what we're talking about. All right, so I said that there's 3 things to learn about the sampling distribution. We know its mean, we know its standard deviation. What about which population distribution is the sampling distribution of p hat? Meaning it's going to probably take on a certain shape, okay? What is that shape going to be, okay? Is it going to take on a particular meaning like bell-shaped, or maybe is it going to be skewed right or skewed left? If it's bell-shaped, it's probably going to be normal then, or approximately normal. All right. So we'll see. So with regards to the sampling distribution of p hat, there's basically one simple rule. Okay. And this rule is really important. So it tells us if both n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10, then this what happens is that the central limit theorem applies. And the sampling distribution of p hat is approximately normal. So the central limit theorem, all right, which we're going to designate as the CLT, okay, because we're going to write this quite a bit. So if you ever see CLT in the future, we're talking about the central limit theorem, says that as long as we have a fairly large sample size, and we can justify it being large enough if we multiply that times p. We also multiply it 1 minus p, that as long as both of those are greater than or equal to 10, That tells us that once we put all the p-hats together into one spot, the sampling distribution of p-hat will start looking very much like a normal looking curve. So do you remember that when we were in StatCrunch and we were looking at the binomial and I had p at like 0.1 and p at 0.9 and the sample size was very small, like 10. The one was very much skewed left and the other one was very much skewed right. And then I increased the sample size greatly. I increased it like to say 1,000. Then all of a sudden this beautiful looking bell-shaped curve occurred for the probability distribution. And the reason why that happened was because of this, the central limit theorem. The central limit theorem. We couldn't do a lot in statistics without the central limit theorem. And so this is an important thing in statistics. Now, I want to point this out to you right away. Okay, the central limit theorem doesn't apply just to the sampling distribution of p-hat. What we're going to find out is that it applies to other things too, also down the line. All right, and there's different criteria for it depending on the statistic. Here, we have to make sure that n times p is greater than or equal to 10 and n times 1 minus p is greater than or equal to 10. When we get to, say, the sampling distribution of x bar, those criteria will change. Don't get hooked on saying, hey, this is what it always is for every statistic. No, the criteria change when the central limit theorem applies. All right, so we have to memorize this, okay, with regards to the sampling distribution of p-hat. So I was just reminding us about the whole StatCrunch thing. Okay, there. Now, if students ask sometimes, well, what happens if the central limit theorem doesn't apply? What is p-hat then? Well, p-hat is would be binomial, and the problem is that when we do inferential statistics, using the binomial is kind of tough at times. In one instance, it's extremely tough. However, using normal things, meaning this, like say the standard normal to figure things out, it's so much easier. Okay, it's so much easier, and so we prefer then to just go ahead and say that things are approximately normal and use the standard normal to figure stuff out in it with regards to inferential statistics later on. Well, let's move on. Kind of belaboring the point here. So the proportion of all U.S. females between the ages of 16 and 24 that routinely played video games is 0.2. Suppose we repeatedly sample 400 U.S. females of this age randomly. So that means a success would be finding a female that plays video games routinely. P is equal to 0.2 because I said the proportion of all U.S. females. So that's P. And that's 0.2. Suppose we repeatedly sample 400 U.S. females. All right, that's N. Question is, what is the probability distribution or the shape of the sampling distribution of p-hat? Well, we got to ask ourselves, does the central limit theorem apply? And let's see. Let's take a look here. N times p, that's equal to 400 times 0.2 or 80, which is greater than or equal to 10. And we have n times 1 minus p, which is 320, which is certainly also greater than or equal to 10. And that means since both apply, all right, the central limit theorem applies here, and the sampling distribution of p-hat is approximately normal. That means when we put all the p-hats together into a histogram, it's going to turn into a nice looking bell-shaped curve. B, what is the mean of the sampling distribution of p-hat? Well, what we find out is that that in value is equal to lowercase p. What was lowercase p for the problem? It was 0.2. That's it. That's all you got to do. Third thing, what about the standard deviation of the sampling distribution of p-hat? All right, So what we found out is that that's p times 1 minus p over n. And then we take the square root of that. Okay. Oh, we're not going to draw a graph yet. We got to actually calculate what that is. That turns out to be 0.02. 0.02. Okay, when you do the math there. All right, I'll let you do the math, all right, in your calculator, but this standard deviation turns out to be 0.02. Now we're going to draw a graph. Believe it or not, drawing the graph is probably the most important thing that we have to do here. Drawing the graph is the most important thing because you get to visualize what the heck we're talking about. And that's important. Please pay attention to this next step here that we're going to draw a graph now. All right. So I put up in the corner here that p hat is approximately normal. Excuse me, the sampling distribution of p hat is approximately normal, has a mean of 0.2, and its standard deviation is 0.02. So we got 0.2 and 0.02. So here I drew a bell-shaped curve. Why did I draw a bell-shaped curve? So I drew a bell-shaped curve here because the sampling distribution of p hat is approximately normal. So these are all the different possibilities for p hat. So technically, if I was able to do this, this is very hard to do this in with these slides, but this axis should have p with a hat over the top of it and parentheses to, and so we're recognizing that this is the sampling distribution of p hat. So these are all the different p hats that we can possibly get. All right, and we drew a nice bell-shaped curve for it. Its mean is 0.2. Well, what is the mean of any bell-shaped curve? Where's it going to be located? It's going to be located smack dab what? Right in the middle. So that's why we put 0.2 right in the middle. And then the third thing is that the standard deviation turned out to be 0.02. So, all right. So let's go out one standard deviation in this direction, 2 standard deviations, 3 standard deviations, and then go out one standard deviation here. Remember, it's 0.02. Another standard deviation here, another standard deviation there. And now we have our sampling distribution of p hat drawn. So what this is representing is all the possibilities for p hat. So notice, let's take a look at our graph here. Actually, I'm going to get rid of my all that and get back into the slideshow. All right, so I got rid of all my drawings there. So what this is suggesting to us then is that when we go ahead and sample, all right, it's most likely we're going to get a p hat located where? Most likely we're going to be getting a p hat located right here in the middle because this is where most of the p hats are going to be located. And the further we get away from the middle, the less likely it is that we're going to get a p hat out here. So it's likely that we're going to get a p hat around 0.2 and less likely to get a p hat out here at like say 0.25 or 0.26, or for that matter out here at 0.14 or 0.15. So if the true population proportion p is 0.2, we don't expect our p hat to be too far away from that. That's basically what we're saying here. Now, to quantify all of this, we can now apply basically the empirical rule. You could also use the standard normal table to figure this out more precisely, but let's just use the empirical rule. So if we went out one standard deviation in both directions, what percentage of all the p hats will be within that from this minimum of 8.18 to this maximum of 0.22? Well, 68% of all the samples with an N of 400 will produce a sample p hat between 0.18 and 0.22. So 68% of all the samples is going to produce a p hat between these two values here. It's as simple as that. Well, what does the second part of the empirical rule say? Well, let's go out one more standard deviation. How much of the data is between those 2 points? 95%. So about 95% of all samples with an N of 400 produce a sample proportion p hat between 0.16 and 0.24. Thirdly, about 99.7% of all samples with an N of 400 will produce a sample proportion p hat between 0.14 and 0.26. So if we go out one more standard deviation, okay? And so what this tells us is that if the population proportion p is 0.2, it's going to be extremely rare to get a p hat that is what, less than 0.14 or greater than 0.26, because there's so little data out there. Mathematically, it's going to be very hard to basically randomly happen. Okay, where most of the p hats located? Smack dab right in the middle here. Let's do one more, just to make sure that you got it. Okay. So the proportion of all voters that voted for President Obama in his reelection was 51.2%. Suppose before the election, a news organization does a political poll of 1,000 potential voters. Assume this was done repeatedly. And a lot of times it is by different news organizations. Okay, certainly even if we put them all those samples from all the news organizations, certainly we could not possibly create the sampling distribution of p hat because there's a whole bunch of different p hats out there. Okay. However, we can theoretically think this through. All right, so what would be a success? Finding someone that said they would vote for President Obama. That means lowercase p is what in this problem? It's 51.2% or 0.512. N is equal to 1,000. So let's create the sampling distribution of p hat. What's the three characteristics that we always want to look at? It's mean, standard deviation, it's probability distribution. Let's start with the probability distribution of p hat. Well, we've got to ask ourselves, does central limit theorem apply? Certainly it does here, right? N is 1,000 times p of 0.512. We get 512. That's greater than or equal to 10. Check mark. We do exactly the same thing over here. We get 488. It's greater than or equal to 10. Check mark. Both of them apply. That means since both apply, the central limit theorem applies, and the sampling distribution is approximately normal. And we don't have to look at binomial things at that point. Turns into this nice, beautiful looking bell-shaped curve. B, what's the mean of the sampling distribution of p hat? We know its value should be whatever lowercase p is. What is lowercase p? 51.2% or 0.512. Simple as that. C, what is the standard deviation of the sampling distribution of p hat? We go and calculate it. It turns out to be 0.0158. Hopefully I calculated that right. So now we got the three components here, right? Got the three components. And so what I did was to make things a little simpler, what I've done here is that I think I made the standard deviation, I rounded it to say 0.016 so we don't have to get too crazy with stuff with the decimals. But notice here's the sampling distribution of p hat. These are all the different p hats of size 1,000. If there was a different size, say 100, the sampling distribution would change. All right, the sampling distribution would change. Actually, we should talk about that before we end this video presentation today. We'll get to that here in a second. But let's focus in on this. So notice 0.512 is, that's lowercase p, that's the mean. So we stuck it right there in the middle, okay? And then we went out a standard deviation, 2 standard deviations, 3 standard deviations, 1 standard deviation, 2 standard deviations, 3 standard deviations. So when you go ahead, when these news organizations sampled 1,000 people, and they did a really good job of mimicking the population, meaning age, political parties, let's say religions, races, so on and so forth. Okay. When they go ahead and sample, all right, when they go ahead and sample, when they sampled the percentage of people that were going to vote for Obama that year in his reelection, okay, they probably got a lot of their samples to come out to right around 51.2%. Why? Because that's where most of them are located. They probably didn't get too many, so it would be really, really kind of bad luck to get something out here, okay? Because remember, it's randomly done, so it would be kind of bad luck if you got something way out here, or if you got something way out here, all right? Could that happen? Yes, but most likely they got something in between here and here, all right? Nope. So let me get rid of all my markings here. Let's get back into the slide. So it says here about 68% of all samples with an N of 1,000 will produce a sample proportion between what? Between here, right, and here. So 68% of all the samples are located within one standard deviation of the mean. Makes sense because it's bell-shaped, it's normal. So we can apply the empirical rule. So 95% of all the samples will produce a p-hat between 48% and 54.4%. And finally, 99.7, practically all of them will be between 46.4% and 56%. And if you wanted to see an article with regards to not necessarily sampling distributions, but just the election in general, at the general election, there it is. All right. So I want to bring up something before we leave. All right. So notice in the formula for the standard deviation of the sampling distribution of p hat, notice what's in the denominator, n. N is in the denominator. So that means as n increases, what's going to happen to the standard deviation of the sampling distribution of p hat? Is it going to go up or is it going to go down? Is it going to increase or decrease? So as n increases, the standard deviation is going to go down, down, okay? So that means that, so two things. The first thing is that we already talked about this, is that we get a different sampling distribution for different sample sizes. Because, why? Because the standard deviation changes, the shape of the sampling distribution changes. Two, as n increases, what happens to the standard deviation? It goes down, and visually what's going to happen? It's going to do what? It's going to visually get more compact because the standard deviation is going down. So as n goes up, standard deviation goes down, and the graph is going to get more and more compact. And where's it going to get more and more compact around? P, in this case, the parameter. So to wrap this all up, all statistics vary from sample to sample, and we have to investigate when we have a new one, okay? So in the next section, we're going to look at the sampling distribution of X bar and see how that plays out. And what are we going to look at? We're going to look at its mean, its standard deviation, and its probability of distribution. All right? So thank you for your time today.